In this video, I want to give an example of a function that's differentiable, but whose derivative is not continuous. And this is not a very easy example to come up with, because most of the time in practice, if you take a function and take its derivative will itself be differentiable, and you'll have no problem differentiating over and over and over again. However, there are functions out there where the derivative exists, but once you take the derivative, that function does not have a derivative. So let's look at an example. So let's say I have this function f of x, which is defined to be x squared times sine of 1 over x, if x is non-zero. Now this function, x squared sine 1 over x, is obviously not defined at x equals 0 because I can't plug in 0 in the denominator here, right? So I will just define f of 0 to be 0. Okay, so let's take a look at what the graph of this function looks like. So this x squared sine of 1 over x, this might be something that you're familiar with from the squeeze theorem. Since sine of 1 over x is always between negative 1 and 1, x squared times sine of 1 over x is always between negative x squared and x squared. So here's negative x squared, and here's positive x squared. And basically what happens is this function, x squared sine of 1 over x, oscillates between x squared and negative x squared, and it keeps doing that like forever. So it does something like, it just bounces back and forth between these two parabolas forever. And it's undefined at x equals 0, and then you just define f of 0 to be 0. So that's the function y equals f of x. That's what it looks like. Okay, so this is y equals negative x squared. This is y equals x squared. And then the function that I drew that's oscillating back and forth is y equals f of x. Okay, so let's see if we can evaluate the derivative. Does f prime of 0 exist? Well, we have to use the limit definition. Recall that f prime of x is defined to be, if it exists, the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is something that if you're taking calculus, you want to make sure that you memorize and understand what it's saying, right? The numerator tells you the difference in the y values from x to x plus h. The denominator h is just the horizontal distance, and so when you divide, you get the slope of the secant line, and then the limit as h goes to 0 is the slope of the tangent line. Or you can think about it as the instantaneous rate of change, right? Without the limit, that would be the average rate of change from x to x plus h of the function, and then as the time interval, or as h goes to 0, then the average rate of change approaches an instantaneous rate of change, and that's the derivative. So anyway, so let's use this definition to figure out f prime of 0. So we're plugging in x equals 0, so we want to figure out the limit of f of 0 plus h minus f of 0 over h. Does this exist? Well, let's see. F of 0 plus h is just f of h. Now h is not 0, right? H is approaching 0, but h is not 0. And so therefore, when I have this piecewise function, my f of h, what do I look at? I look at this, right? Because Here I want my h to not be 0. So I want h squared times sine of 1 over h. That's my f of h. And now I subtract f of 0, which is defined to be 0, and then I divide the whole thing by h. And that gives me the limit as h goes to 0 of h squared sine of 1 over h all over h. And now the h's cancel, and so I have h times sine of 1 over h. So I'm trying to find the limit of this as h goes to 0. And hopefully we know how to do this. So how do we do this? We can use the squeeze theorem, right? Now, in contrast to what we had before with the h squared, here we just have h. And h is a bit more complicated because we have that we have sine of 1 over h is always between 1 and negative 1, right? However, okay, we want to multiply everything in the inequality by h to get the h sine of 1 over h in the middle. However, the issue is that if h is negative, then the inequality signs switch, right? So if h is positive, okay, then there's no issue. We have negative h is less than or equal to h sine of 1 over h is less than or equal to h. If h is negative, then what happens is we have negative h greater than or equal to h sine of 1 over h, which is greater than or equal to h. Now in this case, we can apply the squeeze theorem to each of these inequalities. So from the first one, okay, if h is greater than 0, well, then we can take, so we have the limit as h goes to 0 from the right of h equals 0, and the limit as h goes from 0 to the right of negative h equals 0, right? I'm taking the limit from the right of each of these and showing that they're the same. Therefore, the limit from the right of the middle must be 0. So by the squeeze theorem holds for one-sided limits. Okay, it's not just about two-sided limits. So by the squeeze theorem, the limit as h goes from 0 to the right of h sine of 1 over h is 0. And similarly, if h is negative, then we need to take the one-sided limit where h goes to 0 from the left. And now we're taking, let me just rewrite this inequality. H is less than or equal to h sine of 1 over h less than or equal to negative h. So we can take the limit of each of these from the left. This limit is 0, and the limit as h goes to 0 from the left of negative h is 0. So by the squeeze theorem, the limit as h goes from 0 to the left of the inside thing, h sine of 1 over h, must also be 0. And so we've shown that this one-sided limit is 0, that one-sided limit is 0. So let's call this 1 and let's call this 2. By 1 and 2, this two-sided limit must exist, and it's equal to 0. Okay, and this limit is in fact, so finally we can say that this is 0. And this is the derivative of the function f at 0, right? We showed that this limit exists. So f prime of 0 exists and equals 0. So this function f that we introduced at the very beginning is in fact differentiable at x equals 0. Okay, and f prime of 0 is 0. Now let's look at the derivative of this function. Right? So we know that f prime of 0 is 0. What about f prime of like anything that's not 0? Well, in that case, we can use the function x squared sine of 1 over x. Right? So if x is not 0, then f prime of x is, well, if x is not 0, f of x is just x squared sine of 1 over x. And so what's the derivative? We have to use the product rule. So it's the first function, x squared times the derivative of the second. So it's cosine of 1 over x. But then I have to multiply by negative 1 over x squared because of the chain rule. And then plus 2x sine of 1 over x. And I can cancel out the x squareds here and here. And so this is going to give me negative cosine of 1 over x plus 2x times sine of 1 over x. And so therefore f prime of x is equal to negative cosine 1 over x plus 2x sine of 1 over x if x is not 0, and it's equal to 0 if x equals 0. Okay, I have no idea what this function looks like. But that's the derivative. Yeah, it'd actually be kind of interesting to graph this and see what it looks like. But anyway, I claim that f prime, this function, is not continuous at 0. That's because, let's take a look at the limit as x goes to 0 of this thing, right? If this were continuous, if f prime were continuous, then this function would have to approach, this function would have to approach 0 as x gets closer and closer to 0. But what happens, so this is negative cosine of 1 over x plus 2x sine of 1 over x. Now this thing does approach 0 as x approaches 0 by the squeeze theorem. It's just the same thing as we did before. However, this thing most definitely does not approach as 0, because what happens is that as x gets closer and closer to 0, 1 over x is going off to infinity. So, for instance, if you just look at the limit as x goes to 0 from the right of cosine of 1 over x, right? This does not exist because 1 over x is going off to infinity, and cosine, as 1 over x is going to infinity, cosine of that is oscillating between negative 1 and 1. And so the limit doesn't exist. Cosine of 1 over x doesn't, stabilize towards a particular value. And so therefore, right, if you have one thing where the limit does not exist, and you add something where the limit does exist, then the limit of the sum does not exist. Okay. So since this limit doesn't exist, the function is not continuous. And that shows why when you're evaluating, if you have a function like this that's defined to be one thing when x is not 0, and it's something else when x is equal to 0, if you wanted to find the derivative, f prime of 0, you cannot, in general, just differentiate this thing when x is not equal to 0, and then somehow just take the limit as x goes to 0. right? So one example of a faulty reasoning, and this faulty reasoning shows up a lot in kind of casual explanations. So for instance, let's show that f of x equals the cube root of x. This is not differentiable at x equals 0. So the correct way to do it, well, okay, first I'll do the incorrect argument. So the incorrect argument is to take the derivative it's to take the derivative and get, okay, this is 1/3 times x to the negative 2/3, and this is 1/3 times 1 over like the cube root of x squared. And this function is undefined at x equals 0, so f prime of 0 does not exist. Right? Now we can see that this logic is not correct because we showed above in this example, right? If you did the same thing, okay, where is it? Oh, no, it's here. In this example, if you did f prime of x when x is not 0, you're going to get this. But this is not defined at x equals 0, right? This function is not defined at x equals 0, but f prime of 0 still exists. So you can't look at this and say, well, if I do f prime, I get this, and it's undefined at x equals 0, so f prime of 0 doesn't exist. The thing is that this is true. This f prime of x equals 1/3 x to the minus third is only true when x is not equal to 0. And that's the issue. So saying what the derivative is when x is not 0 doesn't tell you what the derivative is, at x equals 0. So the correct way to do this is you have to use the definition of the derivative, which is the limit as h goes to 0 of f of 0 plus h minus f of 0 over h, right? If this limit exists, then the function is differentiable at 0, because that's what differentiable at 0 means. If the limit does not exist, then the function is not differentiable. So you have to look at this limit. Now, what is this limit equal to? So it's the limit as h goes to 0 of f of h, and that's h to the 1/3 power, minus f of 0, that's 0 to the 1/3 power is 0, all over h. And so this is equal to the limit as h goes to 0 of 1 over h to the 2/3. Right? Because I have h to the 1/3 over h, I subtract the exponents. So I get this. And now what happens is, as h, well, you can see that the limit doesn't exist, right? This limit does not exist. Because the denominator, you have the numerator is 1, okay? And the denominator is going off to infinity, right? So that's going off to infinity. No, what am I saying? I'm being ridiculous. This is going off to 0, and so the quotient is going off to infinity. Yeah. H to the 2/3 is going off to 0, so 1 over that. Notice that h to the 2/3 is always going to be positive, because you take the root and then you square it, so you get something squared, and that's going to be positive. So 1 over h to the 2/3 is going off to infinity, so the limit doesn't exist. And you can see what happens if you graph y equals x to the 1/3. It looks like this. And what happens is at x equals 0, you have a vertical tangent line. And the derivative doesn't exist. So this is the correct way to justify why the cube root function is not differentiable at x equals 0, and you cannot just, take the derivative like this and then get something like this, because to do that you have to assume that x is not equal to 0. And where are you assuming that x is not equal to 0? Okay, you have to go back to the definition of the power rule. If you look at how this rule is proven, when you have a fractional exponent, you're assuming that x is not 0. Yeah. Okay, so that's it for this video. Thanks.